In this video, we're going to talk about functions. Now, this is pretty basic, and I realize that a lot of you have known about functions probably since middle school, but we're going to focus on thinking a little bit more abstractly, so I think that there are probably at least a few places in this video where you'll have to think. And for most of you, unless you talked about the Axiom of Choice in middle school, there's probably at least one place where you're going to see something new. First of all, the basic definitions that a lot of you probably already know. If a and b are sets, then a function f from a to b is just a rule that assigns to every element a in a an element in b which we denote by f of a and which is called the image of a under f. We'll denote a function like this by f colon a arrow b, and as usual the set a is called the domain of the function. Now some people like to call the set b the range of the function, but because that can sometimes lead to confusion, I prefer to call the set b in this definition the codomain of the function. I, like most authors, define the range of the function f to be the set of all possible values f of a, where a runs through the set capital A. My notation for this is to write the range as f of capital A, and of course the range is a subset of the codomain, but in general it could be a proper subset. Next, we say that the function f is injective, or one-to-one, if every element in its range is the image of exactly one point in its domain. To put this another way, the function f is injective or one-to-one if whenever f of a equals f of a prime for 2 points a and a prime in the domain, it must be the case that a is actually equal to a prime. Injectivity is just the statement that you can't have two different points in the domain which map to the same point in the range. Next, we say that the function f is surjective or onto if the range is equal to the codomain. In other words, f is surjective or onto if for every b in the codomain there exists an a in the domain with the property that f of a equals b. And finally, a function f is called bijective if it's both injective and surjective. In other words, if it's both one-to-one and onto. I like to go through a few examples, and I'll start with some that are more familiar, just to make sure that we understand the definitions. First of all, consider the function from R to R, defined by f of x equals x squared. In this case, both the domain and the codomain of this function are the set of real numbers. And in this case, we also have a convenient geometric picture, the graph of the set of all points y equals f of x in the Cartesian plane, which we can use to help us to understand the behavior of this function. Now, it's not always the case that you're going to have a graph to rely on, but when you do, then often it's not a bad idea to start by drawing the graph. In this example, the function f is not injective because there are lots of examples of pairs of different x values that map to the same y value. For example, f of negative 1 is f of 1, and in general, f of negative x is f of x. So the function f is definitely not injective. The function is also not surjective because, for example, there's no value of x with the property that when I plug it into this function, I get negative 1. Now, one thing which you might notice about this example is that I could have arranged for the function f to be surjective if I had restricted the codomain to be the set of non-negative real numbers. Similarly, if I wanted to try to make this function injective, then I could have accomplished this by restricting the domain of the function, for example, to be the non-negative real numbers. That's a technique that I think a lot of you have probably seen before, for example, in the construction of the inverse functions of the trigonometric functions. For another simple example along these lines, consider the function from R to R defined by f of x equals x cubed. Now we know from calculus that the graph of this function is a smooth increasing curve that goes from minus infinity up to plus infinity. And in this example, the function f is both injective and surjective. In other words, it's a bijective function. Remember, to say that it's injective means that if you have two real numbers x and x prime in the domain, which both map to the same point in the codomain, then the 2 points in the domain had to actually be the same number. Similarly, to say that f is surjective means that for every point y in the codomain, there exists a point x in the domain with the property that f of x is equal to y. Next, let's consider the function from n to z defined by f of n is equal to n minus 1. In this example, f is injective, and that's pretty easy to see from the argument here. If f of n is equal to f of m for two natural numbers m and n, then by the definition of f, n minus 1 has to equal m minus 1, which means that n has to equal m. On the other hand, this function is not surjective, and that's also pretty easy to see. The range of the function f is the set of all integers of the form n minus 1, where n runs through the natural numbers. In other words, the range is the set of non-negative integers, which is a proper subset of the set of integers. Therefore, the function f is not surjective. Another pretty simple example, let's consider the function from the integers to the non-negative integers, which takes an integer n to its absolute value. I hope it's clear by now that this function is not injective. To show that it's not injective, it's enough just to find a pair of different points in the domain which map to the same point in the range. And of course, -1 and 1 is just such a pair of points, so the function is not injective. On the other hand, this function is surjective because if n is any integer in the codomain, then of course n is also in the domain, and the absolute value of n is equal to n. That means that every element of the codomain is the image under f of some element in the domain, so f is surjective. Now I'd like to try to steer towards some more abstract examples, so I hope you're all finding this clear and easy to understand. In this example, let's let A be the set of 6 colored triangles that you see here. These triangles have appeared in other videos, and they represent the 6 equilateral triangles obtained by rigid motions starting from a given equilateral triangle in the plane. Let's then let B be the set consisting of a green ball, a yellow ball, and a red ball, and let's let f from A to B be defined by the rule that f of whatever triangle you feed into it is equal to the ball in B with the same color as the top vertex of that triangle. In this case, we don't have a graph to rely on, but since both the sets in question are finite sets, it's pretty easy to see what's going on with this function if we just list out all the possible elements of the domain and their images under the function f. Now from this list, it's clear that f is not injective, because for example, there are 2 different triangles on the left that both get mapped to the green ball in B. And it's also clear that f is surjective since all of the elements of B appear as possible values of the function on the right-hand column. Now, in case some people are getting bored, let's try a little more complicated example. In this example, let's let x be an arbitrary set, and for each subset A of x, let's define a function which we're going to call f sub A from the power set of x to the power set of x by the rule that f sub A of any element B in the domain is equal to A set minus B. Let's now ask for what choices of the set A will the function f sub A be injective. It's important here to realize 2 things. The first is that in the statement of this question, you don't have any control over what the set x is. All that you know about it is that it's some set. The second thing to realize is that each one of the functions f sub A depends on the choice of A. For some choices of subsets A, this function may turn out to be injective, and for other choices of the set A, it may not. Now, how are you going to answer such an abstract question like this? Well, I would say that the first step is to think carefully to make sure that you understand the definition of the function and what might cause it to fail to be injective, and then to try to figure out what could cause that to happen. Maybe also work through some examples until you have some idea about the solution. Now, after I thought about this question, I eventually had an idea, and when that idea came to the surface, one of the important observations that occurred to me is that the function f sub A can only map 2 sets B and C to the same set if the intersection of A and B is the same as the intersection of A and C. If you think about it, the function f sub A of B is just taking everything in A and then throwing out everything which is also in B. Now, if there's any element of x which happens to not be in A, then you could either add or remove that element from the set B, and you would change the set B, but you wouldn't change the value of the function f sub A of B. In other words, if there's any element in x which is not in A, then the function f sub A will fail to be injective. To write that out with a little more detail, let's suppose that A is not equal to the whole set x. Well, then there exists an element x in x which is not in A. Now, of course, from the definition, we know that f sub A of the empty set is equal to A set minus the empty set, which is just A. But since the element little x is not in A, f sub A of the set containing the element little x, which by definition is A set minus the set containing little x, is also equal to A. Now we've shown that there are 2 different elements of the domain, which map to the same element in the range. So we can conclude that if a is not equal to the whole set x, then the function f sub a is not injective. That still leaves open the question of what happens when a is equal to the whole set x, but in this case it's pretty easy to understand what's going on. If a is equal to x, then for any element b in the domain, f sub a of b is by definition a minus b, and since a is equal to x, that's just the complement of b in x. Suppose that we had two elements of the domain which got mapped to the same point in the range by the function f sub a. Notice here that I'm not assuming that b and c are different elements of the domain, so I'm not aiming for a proof by contradiction. Instead, I'm going to try to conclude that b has to be equal to c, although maybe saying that is spoiling the surprise. Anyway, if f sub a of b is equal to f sub a of c, then by the definition of f sub a, that means that b complement is equal to c complement. Therefore, the complements in X of both of these sets must also be equal to each other. But since the complement of a set is just the original set, that shows that b has to be equal to c. And it allows us to conclude that when a is equal to x, the function f sub a is injective. That gives us a pretty satisfactory answer to what seemed to be a very abstractly posed question. The function f sub a will be injective if and only if the set A is equal to the set x. Now we can still have some more fun with this example by asking when the function f sub a will be surjective. Here, like before, the first step is to think about the definition of surjectivity in conjunction with the definition of f sub a to try to decide what you think the answer should be. Now for me, one of the crucial observations was that for any element b in the domain, the function f sub a of b, which is just a minus b, is always a subset of the set A. That means, for one thing, that if A happens to be a proper subset of X, then there are some subsets of X in the codomain which will never be realized as values of the function f sub a. To formalize that argument, let's suppose that A is not the whole set X. Well then, we can find an element little x in the set X which is not in the set A. And since X is not in the set A, it means that X is not in A minus B for any B in the domain. Therefore, in particular, the set containing X is not an element of the range of the function f sub a. So if A is not equal to X, then f sub a is not a surjective function. Now, as before, we're left with checking what happens when A is equal to X. And thinking ahead a little, it's not too difficult to understand why, if A is equal to X, the function f sub a is going to turn out to be surjective. To see why, choose your favorite element b in the codomain. Now we want to show that b is actually in the range of the function f sub a. And to see why that's true, just think about what the function f sub a does to a set when a is equal to x. Well, we've already seen this in the previous part of this problem. If a is equal to x, then f sub a of any set is just the complement of that set. So if I want to feed in a set and get out the set b, then I can feed in the set b complement, which is another element of the domain. Since every possible set b is in the range of the function, when a is equal to x, the function f sub a is surjective. So our answer to this question is that the function f sub a will be surjective if and only if a is equal to x. There is one more cool thing that I want to talk about, but before I get to it, let me just quickly tell you a few more important facts and definitions that you're probably familiar with. The first fact is that if you have a bijection from a set A to a set B, then the cardinalities of the two sets are equal to each other. In fact, to be honest, this is really part of most people's definition of cardinality of sets. It's true for finite sets, and it's also true for infinite sets, even with the more refined notion of cardinality that I mentioned in a previous video. The second important fact is that if you have two finite sets A and B with the same cardinality, then a function f from A to B will be injective if and only if it's surjective. This can save you some time in certain proofs because for finite sets with the same cardinality, if you're trying to show that a certain function is a bijection, you only need to check that it's injective or surjective, and the other property automatically follows. I want to emphasize though that the assumption that A and B are finite sets is crucial here, because this result is not true in general for infinite sets. One reason why bijective functions are important is that they allow you to define inverse functions. If f is a bijective function from A to B, then the inverse function, denoted f inverse from B to A, is the function defined by the rule that f inverse of y equals x if and only if f of x is equal to y. The assumption that f is a bijection is important, and it guarantees two important properties of the inverse function. Number one, it guarantees that the definition here actually makes sense, so that the inverse function is well defined. If you think about it, if f were not surjective, then if you tried to plug a value of y, which was not in the range of f, into the function f inverse on the left-hand side, then you would have no way to find a value of x which satisfies the equation on the right-hand side. In other words, f inverse wouldn't actually be defined at such a point. Also, if f were not injective, then it would mean that you could find a point y which was the image of two different x's in the domain. Then, when you try to define f inverse of y, how would you know which of the 2 points to pick? In that case also, f inverse wouldn't be well defined. It's pretty easy to see by similar reasoning that the inverse function is also a bijection. Another definition which I hope is familiar to most people is the definition of a composite of two functions. Let's suppose that I have two functions f from a to b and g from b to c. Then the composite function, denoted g circle f, is the function from a to c defined by g circle f of x is equal to g of f of x. This makes sense because if x is in a, then f of x is in b, so it's something that we can feed into the function g to get out something in c. Now, one thing just to be careful of is that while it is true that the range of the composite function g circle f is equal to the set of all values of g taken at points in the range of f, the latter set may not necessarily be equal to the range of the function g. In other words, it's not always true that the range of a composite function formed in this way is equal to the range of the function g. The reason for this is very simple. It's because the function f may not necessarily be on 2. And if it's not on 2, then it's possible that when you compose g and f, there are some values in the set b which never end up being plugged in to the function g in the definition of composite function. I'll leave it to you to think through the details of that. The final thing that I want to talk about in this video is how to extend the definition of the Cartesian product that we gave in the previous video to form the Cartesian product of an arbitrary collection of sets. You may have noticed in the previous video that I defined the Cartesian product of a finite collection of sets, but I stopped short of trying to define it for infinite collections of sets. Well, if you have an arbitrary collection of sets AI indexed by some indexing set capital I, the Cartesian product of this collection of sets is defined to be the collection of functions f from the indexing set I to the union of all the AIs, with the property that for every little I in the indexing set, f of little I is an element of the set capital AI. The notation that I'm going to use for generalized Cartesian products is the product symbol, but some authors also use the big times symbol here. Now, at first glance, this may seem to be a little different than the way that we define Cartesian products of finite collections of sets, but for finite collections of sets, it's actually just a different notation for the same thing. I'll show you a couple of examples to illustrate what I mean. For the first example, let's suppose I have two sets A and B, and let me call them A1 and A2, so that my indexing set is the set consisting of the indices 1 and 2. The definition of the generalized Cartesian product of these sets defines it as the collection of functions from the set consisting of 1 and 2 to the union of A and B, with the property that the value of f at 1 is an element of the set A, and the value of f at 2 is an element of the set B. Now, if you compare this with our original definition of the Cartesian product of A with B, which was the collection of all ordered pairs A comma B with A and B, you'll see that they really are just different notations for the same object. In the Cartesian product on the bottom, the first element of this ordered pair corresponds to the value of the function f at 1 in the definition on the top, and the second element in the ordered pair corresponds to the value of f at 2. What about if I have an infinite collection of sets? For example, what about if my indexing set is the set of natural numbers, so that for every natural number n, I have a set A sub n? Well then, the Cartesian product of the ANs is defined to be the set of all functions from the natural numbers to the union of the ANs, with the property that for every n in the natural numbers, f of n is an element of the set AN. If you want, you can think about this as the set of all infinite ordered tuples of elements AN, where each little an is an element of the set big AN. The A1 in the object on the bottom corresponds to the value of the function at 1. The a2 corresponds to the value of the function at 2, and so on. So the Cartesian product in this case is really the set of all infinite sequences a1, a2, and so on, where each an is taken from the set an. Well, now I want to show you an example of how things can get complicated. The first thing that's complicated in this example is the choice of indexing set that I'm going to use. For my indexing set here, I'm going to take the power set of the set of real numbers. In other words, I'm going to take the set of all subsets of the real numbers, but I'm going to remove the empty set from this collection. So the indexing set is the set of all non-empty subsets of the real numbers. Now, each element of this indexing set is a non-empty subset of the real numbers. So for each s in the indexing set, I'm going to define the set a sub s to just be the set S. The question is, what does the Cartesian product over all s's and I of this collection of sets look like? Well, of course, we have the definition, which says that the Cartesian product is the set of functions from this indexing set to the union of the as's, with the property that for every element s of the indexing set, the value of f at s is an element of the set S. Remember, S and AS are the same here. Now here's a question for you. What does a typical element of this set look like? In fact, to ask an even easier question, can you even tell me what one element of this set looks like? The issue here is that it's not clear how to define a function f which can take as its input an arbitrary non-empty subset S of the real numbers and then output an element of that set. This kind of problem has a long history in mathematics, and it's not something that should be taken for granted. In fact, for the sake of people who know about this, I'll mention that the non-emptiness of the Cartesian product for arbitrary collections of non-empty sets AI is equivalent to the axiom of choice. I don't have a lot of time to talk about this now, but I'll just say that the axiom of choice is a somewhat controversial axiom in the foundations of mathematical set theory, which can be used to mathematically prove certain results, like the Banach-Tarski paradox, which seem to most people to be paradoxical, or at least non-physical results. Anyway, even though this is sort of lurking in the background, there's really no problem with the definition of Cartesian products of finite collections of sets. And for the most part, that's all we'll end up dealing with. Okay, that's the end of this video. Thanks for watching. The next video, which is going to be the last of our preparatory videos, is going to be about properties of the integers.